Hello, I'm Mike McCulloch. I've come to this local lake to try and explain one of the major points about quantized inertia, in that in the theory only waves you can fit within the medium are allowed. So if you look at the lake behind me, it might be, I don't know, it's a few tens of meters across maybe. That means that the waves longer than that just can't be allowed within the lake. They won't fit. And so the spectrum of waves able to form on the lake is limited to waves shorter than that. So quantized inertia is the same, but instead of talking about water waves, we're now talking about quantum waves. So this brings me back to, brings me to Exhibit A, which is this badminton shuttlecock, which has seen better days. It's been used a lot. I enjoy badminton. But the important thing I want to point out is that the holes at the bottom of the shuttlecock are large, whereas those at the top are small. So this means that more quantum waves will be allowed at the bottom of the shuttlecock than will be allowed at the top. Because if you like, the lake here, the area of each of these holes is larger, so the lake is larger, so more waves are allowed. And at the top, the lake is smaller, so fewer waves, only shorter waves are allowed. So this means that if you put this shuttlecock into a vacuum, a quantum vacuum, and you make things accelerate within it, for example a current, then what will happen is that more waves will be allowed at the bottom, fewer at the top, and that will mean there'll be a gradient in the quantum vacuum. More waves below, fewer above, means that there'll be a push upwards, so it should lift up if the accelerations you apply are strong enough, and so the quantum vacuum becomes intense enough. Okay, well, I hope you've enjoyed this quantized inertia short, and I'll see you next time. Goodbye.